We fixed it. Okay, so yes, we're SAT 5, Applications of Integration. Now this was a very short unit. We had 5A, 5B, 5C and 5D. And so those were the topics. In 5A we're just doing area under the curve, 5B area between functions, 5C was kinematics, and then 5D was problem solving. Now the problem solving questions are reasonably common, like we're finding area under the curve to represent some quantity. So we'll go through that one at the bottom here. That'll be a good indication of some previous exam questions as well. They often involve rate of change, water flowing out, or this circumstance is about traffic. There was one of those that popped up in the exam a couple of years ago. Okay, so I think we're pretty happy with area under the curve. Let's do area between two functions. So we've got find the area between the function y equals x squared and the line y equals 9. So it helps to just sketch them. Here's the line y equals 9. Here's the function y equals x squared, and we want to find this area that's bound by both of those functions. So the first thing we need is the points of intersection. We need to know when does the function x squared equal the function 9. When are they equal? Square root both sides, and we get positive 3 and negative 3. That's going to be our upper and lower boundary. And so then the calculation we're going to perform is the integral from minus 3 to positive 3 of the top function, which is 9, take away the bottom function, which is x squared. Now we can perform that in our calculator. We can even perform this in the graph mode of our calculator. If we graph both, we can just g-solve the area there too. Another calculation that, because of the nature of this graph, because it's a quadratic that's symmetric about the point of origin, you could even do 2 times the integral from 0 to 3. All right, and so that's going to give you twice that area because it's symmetrical. So that's another calculation you can perform as well. That one might be a little bit easier because you're not substituting a negative 3. Anyway, I'll process the top one here. So we'll have, this is probably the most sensible way to do it. And so what we'll have, we'll integrate with 9x, take x to the 3 on 3, from minus 3 to 3. Sub in the upper and lower boundary, 9 times 3, take 3 to the 3 on 3, and then take away minus 3, take minus 3 on 3. And then we just need an answer, okay? You don't need to show your working out for it. 36, thanks, please. And it's an area that will have units squared. All right, on to 5C. We have kinematics. We have a particle has a velocity function, 1 take 2t, as it moves in a straight line. Find the total displacement, find the total distance travelled in the first second of motion. Okay, so if we have 1 take away 2t, that's the velocity function. Now, total distance means how far does it move to the right plus how far does it move to the left. So we're going to need to draw a sign diagram here to anticipate when is it changing direction, what's going on with this particle. So if we draw a sign diagram of this function, it's the equation of a line. It has a root at half, or 0.5, and it has a negative slope, which means it's coming from above to below. So all of that, we can get that straight from our calculator, just the graph of the v of t function, to get its sign diagram. Now what this tells us is that it's moving to the right, and then it starts moving to the left. Okay, so for total distance, what we want to know is we want to know what's the area under the curve. Like if we graph this function, this is what it's going to look like. Okay, we're going to want to know what's this area, that's how far it's moved to the right, and then what's this area, that's how far it's moved to the left, and we'll add them together. It is going to be symmetrical as well, so we can calculate one and double it. So if we look here, it's a triangle, it has a base of half and a height of 1 because that's the y-intercept. And so the area of the first triangle is going to be 0.5 times the base times the height. So that's 0.25 here. And then the same with our second triangle here, 0.25. All right, so the total distance travelled then in the first second from time is 0 to time is 1, the total distance is 0.5 units, centimetres. Now, of course, we've done that using like a graphical solution. What we mean by that is we've solved it in terms of areas of triangles. One way we could do this is to do the integral from 0 to 0.5 of v of t, and then we're going to plus it to the negative integral from 0.5 to 1 of v of t. This one has to be negative because it's area below the x-axis. Both of those are exactly the same calculation. Okay, so that's 5a. And then 5b, find the displacement of the particle. Well, displacement just means what's its position from where it started. So what we're doing is we're moving 0.25 to the right, 0.25 to the left. Okay, if we're moving 0.25 that way, 0.25 this way, our displacement is 0. So we can say S of 1, the displacement when time is 1, is 0. Very good. Okay, on to number 6 then. We have the rate of traffic flow past the pedestrian crossing between 8 and 8:30 is given by this equation in cars per minute. Okay, so we're given a rate function. We're not given a quantity, we're given a rate function. The graph is shown alongside. Find the rate of traffic flow at 8:20. All right, so what this means is it wants us to find R of 20, okay, where T is time in minutes after 8 a.m. So all we would be doing, and I think the best thing for us to do here is going to be to graph this function, because I'm anticipating we're going to be doing a few calculations with it. So let's pull our calcs out, put our graph number there. Plus 4x plus 40. We've even got a V window there that we can copy. So copy that V window. We're going from 0 to 30 on the x-axis and 0 to 50 on the y-axis. Gorgeous. And we will G-solve or trace. We want to know when x is 20. What's the y value? The y value is 20. So R of 20 equals 20. And remember, R is in cars per minute. So 20 cars per minute at 8:20. Good, that's part A. Part B, use the graph to estimate the time when the traffic flow is greatest. So, based on what we've got here, the traffic flow is greatest at what, 8:05 a.m. That's when that max occurs. So that's part A. Part B, so all I'm doing is looking at the graph. We can G-solve the max, and we're just looking at what's the time value of the highest one. Shade the region corresponding to R of t, the integral from 10 to 15 of R of t. All right, so we're giving you the graph alongside. Looks like this. And 10 is here, and 15 is here. And so I'll just shade that region. Very good. And explain what this represents, okay? This area tells us, all right, so as a general principle, we have a rate function. Area under a rate function is a quantity. Our rate is cars per minute, which means that area under this function is going to be the quantity of cars. So this area tells us how many cars pass through between, and the time is 8:10 to 8:15. Very good. how many cars pass the crossing between 8 and 8:30? So for part D, this is just going to be an integral from 0 to 30 of R of t. Alright, where you can save time, okay, it would take you, what, at least 15 seconds to write out the whole R of t, or it takes you 2 seconds to just write out those letters. So we can do that, that's absolutely appropriate because we're given the label R of t function. And I'm just going to perform this calculation on my calculator because I've got the graph here. I'm going to go G-solve, integral, just the basic integral from 0 to 30. Just going to shade all that area for me. And it's going to tell me we had 1,031.25. So we round to the nearest integer, 1,031 cars. Bang. All right, so that's our applications of integration questions. Now we have recently done continuous random variables, haven't we? So what we might do, I think I'll leave these 2 questions for you for continuous random variables to have a bit of a go at. We could probably do them now. And then it's up to you where we're going to dedicate our efforts. We've given you the tests for the apps of integration already and the continuous random variables.